This presentation is about estimating the population mean, assuming that we already know the population standard deviation. That assumption that we already know the standard deviation is not very realistic. And we'll be able to drop that in a later section of the workbook, but it simplifies the problem to assume that we know the standard deviation. So the idea is we're not able to know the population mean exactly because it's a huge population. We're going to get a sample mean, and our goal here is to calculate a margin of error so that the sample mean is probably not more than that distance, that margin of error away from the truth. Okay. And the way the workbook discussion is set up, it basically all I've written here is just that your instructor will solve the following problems on the board, and so I'm recording that now on paper as a replacement for the classroom exercise. So here's the setup. So the story is that the time in minutes taken by a biological cell to divide into two cells has a normal distribution, and we're assuming we know the true population standard deviation sigma to be exactly 3.5 minutes. And then the question we want to solve is to find the margin of error for estimating the true population mean time at the 90% confidence level with a sample size of 64. So the idea is we would go out and get 64 randomly selected cells, see how long it takes each one of them to divide, get the average, that's the sample mean, and then the population mean is probably close to that. We're going to calculate the margin of error. Okay, so first let's draw a picture of the information that we have. And because of the central limit theorem, we know how the sample means are distributed. So what I've drawn here is when you consider all the possible sample means for different samples of size 64, different groups of 64 cells, that the distribution of all the sample means that you might get has the normal shape, and that's because of the central limit theorem. That says if the original variable, the x, the division time of a single cell, if that was normal, then so is x bar. So we've got it for that reason. The central limit theorem says even more than that. It says if the sample size is large, then the distribution of x bar is normal. So x bar is really normal in this case for two reasons: the large sample size, bigger than about 32, and x was normal in the first place. So here's the distribution, and what I've marked in orange here is the margin of error. We don't know this true mean. This is the population mean here in the middle. Central limit theorem says the mean of the x bars is the same as the mean of the original x. We don't know the mean, but it's in the middle. And 90% of the time, your sample mean will fall pretty close to that. The distance, the margin of error, is this orange distance here. That's E. And first, I just want to figure out how many standard deviations is that, and then we'll figure out how many minutes that is. Okay. So, well, So first, just in standard deviations, look at this z with a little asterisk there. That's the critical z-score, or the critical value of z is the way you say it. So if you, the x bar 64, the average time to divide, that's in minutes, but you could go along the horizontal axis here and convert any number of minutes along the axis. You could convert into standard deviations. And so what the z-star is it's however many minutes this is right here at the edge of the middle 90%. Z-star is just so how many STDs above the mean, how many standard deviations above the mean is that? And so we can find the z-star real easy. There's this function in Excel for a standard normal variable. You can find a critical value. The way the function's written, what you have to put in, you have to give this function all the area to the left of the point you're looking for. So that's the 90% in the middle plus the 5% on the left edge. And the Excel function that does this for you, it's norm.inv, norm.inv. So you put in the 0.95, and the z-scores have a mean of 0 and a standard deviation of 1. That's nothing to do with the normal distribution. That's just because you're using standardized units of measurement. Whatever was the shape of the distribution, if you convert the units of measurement to STDs, the mean is 0, just because with the STDs you count from the middle. So the mean is 0, and the standard deviation is 1 STD, 1 standard deviation. Like by definition, that's how many minutes 1 STD is. So it's okay. So you use Excel to find the edge of the middle 90%, and it'll tell you that's at 1.645 standard deviations. So that's the margin of error in standard deviations, 1.645 of them. But the question is, how many minutes makes 1 STD? Well, the central limit theorem tells us that the standard deviation of the sample mean is the standard deviation of x divided by the square root of n. That's true regardless what shape the distribution has. It's true for the normal distribution, but it's true for any other distribution as well. So the standard deviation for our distribution here, standard deviation of x bar 64, is from the problem, or the original problem we had. We were given a standard deviation of 3.5 minutes. We were given that the number of cells was 64. And we were given this confidence level, the 90. That's where we got the 90% in the middle. So I'll take my 3.5 minutes over square root of 64. And this many minutes that many minutes is one standardized unit, one STD. So, what's our margin of error? It's 1.645 STDs, and how many minutes makes one STD? This many. So we're just going to multiply to get our margin of error. Now see, it's our 1.645 STDs times the original standard deviation over the square root of n. Okay, so this is the formula, you know, to memorize for how you find the margin of error. That's it. So we have our z star times 3.5 minutes over square root 64. So that's 1.645 times 3.5 and then divided by 8. And so what we come to is the margin of error is 0.72 minutes. So, going back to the exercise in the workbook, I'm going to write 0.72 minutes right there. So now, what we figured out is that there's a 90% probability that the distance between the population mean and x bar is not more than 0.72 minutes. Okay. So the story continues. We go out and we get a sample of 64 cells, and for just those cells the average division time was 31 minutes. Okay. So the population mean is probably not more than 0.72 minutes away from the 31. So it's somewhere probably between 31 minutes minus 0.72 and 31 plus 0.72 minutes. Okay. Yeah, you can do the arithmetic yourself. On a test, I'd probably want you to finish out the arithmetic. I'll just leave it this way so you don't forget where it came from. And now, well, what if you wanted to know the population mean, mu, more accurately? Suppose that a margin of error of 0.72 minutes leaves too much error. Suppose you think, I wish I could be 90% confident that I knew the mean to within plus or minus half a minute. If you wanted the E to be half a minute instead of 0.72 minutes, now the question is, how big would your sample need to be? So, it's a little algebra problem. So now we want to find the n in order to make the E to be 0.5. There's the formula for E. It says E equals, but I want to rearrange that to make it say n equals. And then I'll plug in the numbers and find out what n is, my sample size n. So I want to try to get the n by itself. I'm going to multiply both sides times the square root of n. Okay. So I'll multiply here times the square root of n. I'll multiply here times the square root of n. Waka waka. Well, I don't waka waka. What I do is waka waka here. Well, this one's still there. So I come to e times the square root of n equals z star times sigma. Okay. I'm still trying to get the n by itself. So I'm going to divide both sides by e. I'll do divided by e. I'll do divided by e. So I'll come to the square root of n is z star times sigma over e, because these guys canceled. I don't want the square root of n, I want n itself. So I'm going to square both sides. And when I square the square root of n, that's just n. So there you go. So some of the books, especially since, like in this class, algebra is not a prerequisite, a lot of books will give you this formula for e over here, and they'll give you this formula for n separately as just two separate facts. And if you want to memorize them that way, that's okay. For me, I guess I like to memorize fewer formulas and kind of rely on, you can always rearrange a formula into different forms. So anyway, so now all I have to do is just plug in the numbers. I want the e to be 0.5, and we had the z star from the previous calculation, and the 3.5 minutes was the given standard deviation. So I just put those numbers in my calculator and work out everything on the inside first and then square it. And I get 132.6, but now n is the number of individuals, cells in this case, in your sample. It's going to have to be a whole number. So I can't stick with the 132.6. I need to round to a whole number. And the rule is you always round up. Okay, even if that had been like a 0.4, you would still round up. And the reason for that is you want to be at least, in this case, 90% confident that the error is not more than half a minute. If you round down, you'll be a little less confident. So you round up, regardless what the next digit is here. Okay, so I'll just fill in the answer over here. 133 cells on tests, and always asking you to include the units of measurement on everything. Let's see, did I do it? No, I didn't do it here. See, 90%. Okay. And that's it.